Okay, so the process of rationalizing the denominator is the process of getting rid of the square root that shows up in the denominator, because mathematically we say that that's just ugly to leave a square root in the denominator. And you'll run into it a lot more when you get into pre-cal, and you'll see why it's important to get rid of it then. But it says when simplifying radicals, if one has a fraction with a radical, and of course this is a radical in the denominator, the process of ridding the denominator of its radical is called rationalizing the denominator. And then I remind you of a couple things that we're going to use. Remember that squaring and taking a square root are opposite operations. So if I take the square root of a number that I've squared, I'm back at whatever that number is. And the other property that's at work is if I multiply a number by 1, we're back at itself. But remember that 1 doesn't have to look just like a plain old 1. Anything divided by itself evaluates to 1. So a divided by a is 1, pi divided by pi, a squared divided by a squared, or the one that's going to become important to us is the square root of a, any number a, divided by itself is also equal to 1. So here's how this works. If I end up with an answer such as 15 divided by the square root of 3 when I'm working with my special right triangles, and I see that I have that square root of 3 in the denominator, I need to get rid of it. But I get rid of it by multiplying it by 1, but not any 1. I take that square root and create a fraction of whatever that square root is over itself. Square root of 3 over square root of 3 is 1. So what I'm doing is I'm multiplying my original answer by 1. But that particular 1 happens to be whatever this number is over itself. So once I set it up like that, then it's a matter of multiplying numerator times numerator. So that becomes 15 square root of 3. Multiplying denominator by denominator. So that becomes square root of 9. But because of the way we've set it up, square root of 9 is a perfect square, which is now just 3. So I no longer have a square root in the denominator. There is one more step though. You look at the fraction that's created of just the numbers, just the coefficients of that square root, and if those numbers can be simplified, you simplify. And 15 divided by 3 simplifies to 5, so the final answer is 5 times the square root of 3. Now the cool thing is, because it's mathematically sound, that if you plug this into the calculator, it's going to give you the exact same value as that. And again, it's mathematically sound because all I did was multiply by 1. I multiplied by 1. And of course, when you multiply by 1, even though the appearance is different, the value is exactly the same. So the second example says, well, what if I had a square root of 2 in the denominator? Well, that would make my fraction the square root of 2 over the square root of 2, the fraction that I'm multiplying my answer by, because the square root of 2 over itself is just 1. So when I multiply 22 divided by the square root of 2, when I multiply it by square root of 2 over square root of 2, it becomes numerator times numerator, which is just 22 square root of 2, denominator times denominator. The two square roots can be multiplied into 1, so square root of 4, which is just 2. So notice, again, no square root left in the numerator. So last job I have is to look at that coefficient and see if it simplifies with the number that's left in the denominator, and it does, because 22 divided by 2 is 11. So 11 square root of 2 is exactly the same as 22 divided by the square root of 2. On the next example, I do have 5 times the square root of 2 in the denominator, but I don't need to get rid of the 5. I just need to get rid of that square root, because numbers in the denominator are fine. Square roots in the denominator are not. So I create my special fraction of the square root over itself, multiply my original problem by that value, numerator times numerator, denominator times denominator. So I'm not doing anything different. I'm just multiplying the two square roots by each other. I end up with square root of 4. Well, the square root of 4 is 2, But now that 5 comes back into play because it was 5 times the square root of 2 times the square root of 2. Well, square root of 4 is 2, so it becomes 5 times 2, or 10 in the denominator. Again, once I do that, I do have to look at the fraction and see if it can be reduced, but this time it cannot. So you have several problems to do for homework. I'm going to look at one of them with you because this one looks like it might be a little bit different, but it's really not. So on that problem, I don't need to get rid of square roots in the numerator, only the denominator. So 12 square root of 3 over square root of 6. Can you think about what are you going to multiply it by? And I hope you said square root of 6 over square root of 6, whatever that square root in the denominator is. So you end up with 12 square root of 18, because you can put the two square roots together under 1, over square root of 36. Well, we know what the square root of 36 is, don't we? That's just 6. So that becomes 12 square root of 18 over 6. 6 goes into 12 2 times, 2 square root of 18, and you think you're finished, but you're not, because square root of 18 can be simplified. Remember, you look for perfect square factors. 18 is 9 times 2. I can take the square root of 9. The square root of 9 is just 3. So 3 times 2, I took that square root, becomes 6 square root of 2. So this problem had a few more steps because I ended up with something inside the square root that could be simplified because the numerator had a square root already, and when I multiplied the two square roots, it gave me something that had a hidden perfect square. That 9 was the hidden perfect square. So there's the final answer for number 18. All right, you're going to do the rest of these for homework, show all your work. There is a pattern. If you can find the pattern completely on your own, you can use it, but be on the lookout for it. But try several problems first to get the hang of it. All right, have fun.